Hey there, everybody. This is Tim Bray. I'm a senior engineer with Amazon Web Services up here in beautiful Vancouver, Canada, which I would show you with a harbor and so on outside, but hey, it's too many photons and it screws up the camera, so we won't. I've got things all tangled up now. Anyhow, so this is the last in our Twitch series on the very many AWS messaging systems. About 2 or 3 months ago, towards the beginning of the year, we realized that AWS has at least 6 different systems which are directed at sending messages around, and that each of them was successful and popular, but maybe it would be helpful to talk to the world about what they're for and why they're different and which one you might want to use. So that's what we've been doing. The screen that you're looking at right now is at aws.amazon.com/messaging, and it's a really good place to start. If you're in a situation where you might want to do some messaging and would like to start upgrading your consciousness. Another thing to do would be to look at some of these things that we've recorded. At the end of the talk, if you just take that URL and put /Twitch on the end of it, you'll get oh, there it is, thanks there. You'll get the recordings of all of these sessions, which may prove useful. Okay, let's get to the subject of today's sessions, which is about messaging with millions of devices. And today I have with me from Seattle, Dinkar Pataballa of our Internet of Things group. And Dinkar, perhaps you could get us started by talking about your role over in IoT and introduce the messaging capabilities that the IoT services have.
Yeah, hey Tim. So this is Dinkar Pataballa. I'm a software dev manager with AWS IoT. I lead the message broker services within AWS IoT. So to talk about the message broker, it's basically a fully managed PubSub service that allows for devices to securely connect and talk to each other, and also to talk to other AWS services. So for the communication part, it uses a PubSub messaging model. So devices can subscribe to topics, and the other devices or publishers can publish on a particular topic, and then the message broker is going to find out who the interested subscribers are and then deliver the message to those topics, to those subscribers. In terms of, whenever we talk about message brokers, we basically talk about protocols. So if you see on the screen here, I'm going to zoom it a little bit. So in terms of protocol support, there is support for MQTT, HTTP, HTTPS actually, and then MQTT over WebSockets. So depending on the protocol that you use, there is a specified set of authentication mechanism and a supported port. So for instance, if you're using the plain MQTT, the supported authentication is basically client certificate based mutual auth. And then the ports that are supported are 8883 and 443.
For those people who don't know, we should probably mention that MQTT is a protocol that came out of the Internet of Things world and is designed to be, first of all, persistent for low latency, unlike HTTP, and also really dumb, designed in such a way that your garage door opener can talk it if need be.
That's right. And the another interesting mix to this is that the AWS IoT message broker integrates very well with other AWS services, be it in the storage world like S3 or databases like DynamoDB, even messaging like Kinesis and SQS through a component called Rules Engine within AWS IoT. So the message broker, so customers can actually create rules. It's like a rule configuration, and when they do that, they're able to kind of pump their data through AWS IoT into these other AWS services. So it's a nice integration that it provides along with just the broker capabilities.
Well, cool. So that's sort of a just the facts approach, but our goal here is, first of all, to convince everybody that we're not crazy for having 6 messaging services, and secondly, to help understand which of the services are the right ones for the application that any particular person might be trying to build. And probably the best way to do that is by example. So for each of these ones, we've tried to take an example application where it's worked out well and explain why. Now, you were telling me that you had been working with Amazon Music to build an app that relied heavily on this. So maybe I could get you to tell us about that. But first, hold on a second. This is Twitch, by the way, and it's interactive. So while we're talking, feel free to shoot any questions you'd like to down the Twitch channel, and we're watching there. And we'll either take it live here by voice or maybe just type an answer into the channel. So feel free to interrupt us at any time. So Dinkar, you want to go ahead and tell us about Amazon Music?
Yep. So Amazon Music is basically a music subscription service for Amazon Prime customers, and Music Unlimited customers. So they basically have like millions of tracks in their catalog that you get access to, and then you can stream music. So one of the things that they did last year was to kind of support live audio streaming of soccer games, especially in the German football league, soccer league. And as part of that, functionality, they wanted to provide an ability to kind of update real time their apps, both on their mobile applications as well as their desktop applications, to get live events as they were happening on the game. So someone scored a goal, or there was a penalty kick, or any of that sort. They would have, and if their customers are using the app, then they would see those live events coming up on the app itself. So that's something that they wanted to do, and I'll quickly share just a second, show the PowerPoint of their game page. So if you look here, this is how their game page would look like. So in this, they basically have a list of games that they have listed, and each of those games have like a status of what the score is, whether it's halftime, full time, or how many minutes has passed in the game. So it's like a summary view of all the games that are happening over the weekend, and that's one page. And then they have the now playing page, which is basically if you go click on one of the particular games that are happening, then in that page you actually get the complete match stats, you get the score, of course, and also like if you click on that play button, it'll start doing the audio stream. So as part of this, what they actually wanted is, if you see in these screens, these scores and the game stats should automatically be updated as they were happening. So in order to do that, they actually decided to use AWS IoT. And the reason why they wanted to use AWS IoT was that it could provide that ability to kind of basically they could have their users subscribe to the game topics, and then when an event has happened, their service would publish a message on that game topic, and AWS IoT can kind of broadcast that notification onto all the devices that are subscribed on that topic. So a quick look at the architecture. So they have these mobile devices and desktop applications. They request their credentials using Amazon Cognito to get tokens, and then temporary AWS credentials based on those tokens, and use those credentials to talk to AWS IoT. So they would subscribe to topics, and then they would also receive live updates once they're subscribed. And this is their backend service, which I just realized my mouse doesn't show up there, but there's the green box with Eve written, that's their backend service, which basically is publishing those live events into IoT, and then the devices receive those messages.
Well, what kind of latency are we talking about?
So they're basically, like on the average, they're receiving from the publisher to the subscriber within 50 milliseconds for just one message. But for the overall fan out, one of the requirements that they had was that if there were a million subscribers subscribed to a single topic, they would want all the million subscribers to receive a notification within 60 seconds. That was a very critical requirement for them to make sure that the customers get a kind of a real-time experience on their apps while the events were happening.
So this is a pretty classic broadcast notification application here. So could maybe Amazon SNS or Amazon Pinpoint have been a candidate for this application?
Yeah, that's a very good point, Tim. So both Amazon SNS and Pinpoint, they're really good at and are very well designed for push notifications to Amazon, Google, or iOS or other devices through their corresponding push notification services. What Amazon Music really wanted here was, live updates on their apps. So something that tells the app that, hey, tick the score to something else, right? So they had basically two options to do that. One, the app could continuously poll for updates, and as the updates happen, the app could refresh and show that new score or data. But that was very hard. It's going to be very hard for the battery on the phone as well as the data usage. So it was not an option that they were looking into. So what they really, again, needed is a backend cloud service that can actually push these updates into the app while the app is running, or even when the app is in the background. And AWS IoT fits the bill well there because with the MQTT protocol, they can open up a persistent connection to AWS IoT Cloud backend, and then the AWS IoT message broker can use that connection to push these notifications down into the device, directly into the app.
I see. Cool. Now, so these are like big fan outs we're talking about here, like big numbers. So how does IoT do that? How does the fan out mechanism work, and how fast can it go?
Yeah, so basically the logic is straightforward. So we have within the message broker, we have what is called as a subscription store, which stores for a given topic what the subscribers are. It's complicated than that, but there's a simple mapping between a topic to a list of subscribers. So when a message comes into the message broker, it essentially looks up in the store to find out who the subscribers are, and then it kind of distributes the message to each of those subscribers. In the case of a large fan out, let's say there are like hundreds of thousands or even millions of subscribers on a single topic, we kind of receive these subscriptions we break down these subscriptions into small chunks or some sort of pages, and then we spin up workers which are basically working on these pages in parallel. And each worker is basically opening up the page, looking at the subscribers, and then kind of distributing those messages to those subscribers. So kind of parallelizing the large fan-outs by scaling out multiple workers to do the work. So you asked about the speed, right? In terms of speed, like I mentioned, what AWS IoT does is, in order to make it very deterministic for our customers on how fast a fan-out takes, what we do is basically when we are fanning out these messages on the outbound, meaning from the AWS IoT cloud to the devices, we fan them out at a speed of 10,000 messages per second. So let's say if you had 1 million subscribers on a single topic, it would take roughly about 100 seconds to deliver all the messages to those 1 million subscribers. But if customers want them to be done much faster, then they could go the route of kind of breaking down those subscribers into multiple topics, or essentially like sharding their subscribers to multiple topics. I mean, it's better explained through an example. So if you look at the screen here, so there are 1 million devices, they're subscribed on some random topic. And when a publisher publishes on that topic at a speed of 10K messages per second, that's what AWS IoT will fan out. So all the devices will receive this message within 100 seconds at the most. But let's say, like even in the case of Amazon Music, they wanted it in less than 60 seconds. In that case, what customers can do is they can actually break down their subscribers into 2 topics, evenly distribute them, and then have their publisher publish into both topics in parallel. And what AWS IoT will do is fan out each individual topic at that rate of 10,000 per second. So essentially, you double the throughput that you need from the system. So in this case, overall, all the devices will get it in 50 seconds because now we are fanning out both those devices within, in parallel and within the 10,000 messages per second per fan out. So that's what this is a trick that customers can do, especially when they will have devices that are growing in number, but their latency requirements are very strict in terms of how fast they want it to be delivered. In that case, they can use this trick to kind of scale horizontally.
So in effect, the output is 10K times the number of topics, 10K per second times the number of topics. So in this particular case, what actual protocol were they using to deliver the messages here?
So Amazon MQ was using MQTT over WebSockets.
So I have a question here. Mr. Scott G, who asks, isn't that going to murder your battery, keeping a nailed-up connection?
Good question. So actually, the MQTT protocol itself is designed for being lightweight on the devices. So you're right. Amazon Music basically keeps a persistent connection from their both mobile applications and desktop applications to AWS IoT with the MQTT WebSockets protocol. And they actually did extensive testing to see like what's the impact of keeping a persistent connection. And what they actually noticed is that with keeping a persistent connection for long periods of time, they actually saw no impact on either the battery or also the data usage. In fact, in order to keep a persistent connection, an MQTT persistent connection, what devices need to really do is send out very infrequent keep alive pings, and these pings are very lightweight too. They're like 2 bytes. So in terms of both the data as well as the battery impact, it's actually very minimal.
Yeah, in a previous life, I was in the Android group at Google, and I think I seem to recall, it's been a while, that while the connection is live, the radio doesn't actually have to be on the device, right? It'll just wake the radio up every so often for the keep alive. So that's why that actually works.
That's right.
And I think that particularly, MQTT is particularly designed to optimize for that case, because what really kills you on the mobile is actually turning the battery on. So you want to minimize the number of times you have to do that. So I think that's why that works. Okay, so since we're talking about MQTT, I noticed that you're using MQTT, and there's the Amazon MQ service that also supports MQTT. Is either of those an alternative for the other in this case?
Yeah, I mean, so Amazon MQ with the ActiveMQ broker that you deploy on an EC2 instance, because ActiveMQ supports the MQTT protocol. So yes, from protocol support there is in Amazon MQ. But other than that, there are differences between the two services. First, basically, AWS IoT is a serverless option. Customers do not have to kind of purchase or provision their EC2 capacity to deploy broker instances, right? The scaling of the broker based on their usage happens automatically behind the scenes without the customer having to kind of play around with it. Customers also don't have to look into the configuration parameters or even the performance tuning that you need to do for an ActiveMQ broker as your usage gets increased, right? So that's the advantage, that it gives you the serverless option to do it. The second difference between the two services is that the scaling factors are very different. So the AWS IoT message broker has been designed to support really, really large fleets of devices. So if you think about this, even the example with Amazon Music, let's say if you have a million customers or millions of devices that you have on the field, and each of those devices, let's say, has tens of subscriptions, you're already talking about billions of subscriptions that this broker has to support. So that's the kind of scale that AWS IoT deals with, and it's designed to support that kind of scale. So those are the differences in terms of scale and in the serverless model. And then the other nuances to it is the authentication schemes are very different between the two services as well. AWS IoT has authentication for client-based certs for each device. There's also fine-grained policies that you can set on each device so that you restrict the access of the device to a certain resources within AWS IoT, like publish only to certain topics or subscribe or receive messages only from certain topics and so on. And lastly, as I talked about earlier, AWS IoT also has this nice integration with other AWS services through the rules engine.
Cool. Now, just to be fair, I should, probably people out there are thinking, well, I'll just use IoT for everything. So let's talk about the other side of that. Since I actually work with the MQ people, we should probably mention that, obviously, since MQ is based on having a broker in the cloud, and the broker is actually, logically a single host, it has a scaling ceiling. So obviously, it's not going to go near the scaling territory that IoT can handle. But on the other hand, it's got a fantastic compatibility story. JMS, NMS, MQTT, AMQP, Stomp. It's got a really, really broad compatibility story for the kinds of things. So if you've got an existing enterprise application that's using, ActiveMQ or IBM MQ or something like that, it's probably quite likely just going to work with MQ and probably not that great with IOTT. On the other hand, if you need to get millions of things out really fast, IOTT is just the ticket. Also, I guess for MQ, we should mention that if you're in a business that's where you have to worry about compliance, MQ has a very, very strong compliance story with a bunch of the well-known acronyms that I'm not going to run through here. So yeah, the fact that they both run MQTT is kind of a side issue. They're really not aimed at the same case at all.
Right.
Now, you mentioned authentication, and I actually wanted to talk a little bit more about that because particularly in the IoT space, authentication gets weird. Because you've got all those dumb low-power devices out there, and you can't really expect them to do SIG v4 to call an AWS API. So what are some of the stories you have to tell about that?
Yeah, I think for Amazon Music, what they use is basically, for the mobile devices and even the website applications, they are using cognito identities to actually fetch tokens. And they use those tokens to get temporary, limited access AWS credentials that they can use actually to connect and use AWS IoT. So that's what Amazon Music uses. But in addition to that, there is support for, like I said, X509-based certs, which allow for mutual authentication. And then there's also the usual support for the IAM users, groups, and roles that customers could use. But if customers don't prefer any of these things and they have their own authentication mechanism that they have, then they can also use token-based authentication and authorization using the custom authorizers. So those are the options in terms of authentication. And you talked about the low-power device, and we continuously kind of stressed, especially for IoT use cases. So if you have a device which is constrained and it's a low-power device, then we kind of recommend customers to use the X509 certs, use the MQTT native protocol, and use X509 based certificates. And even within that, you basically have two options. You can go with the ECC based certificates, or you can go with RSA certificates. And it's known that ECC certificates are less computationally intensive than the RSA certificates. So if you're really constrained on your device, then I would recommend going with the ECC based certificates as an option.
Right. And I suspect that in the process of setting up one of these things, you're probably going to put this much time into business logic and this much time into getting all the authentication wired up and put together. Speaking of time, Amazon Music? How big a project was this? How long did it take them to pull it together?
So once they started talking to us and started seeing AWS IoT as a potential option amongst all the other things that they were considering at that time, they were able to actually spin up a working prototype within 2 weeks for all their messaging needs of their application. And then they spent another 2 weeks to kind of make it prod ready for the messaging aspects. And then they spent like 1 week to do a load test to make sure that their applications are working correctly on the load and so on and so forth. The overall project itself to kind of build this feature for the customers took about 6 months, where they spent time on the backend services, their applications, and all that stuff. But the fact that they were able to quickly prototype with AWS IoT and also like make it prod ready, they were able to spend their time on the other aspects of their application and not really worry about the message broker itself.
Yeah, that's an impressive story, and we do this kind of thing all the time at AWS. Probably, we see something that looks like it's going to be a good idea, and we're going to build the system, and then a bunch of guys go off in the corner and prototype the hard parts to prove that it can be done. And sometimes those prototypes make it pretty well straight into production once they're proven to work. Of course, then you have to get the auth right and the metering right and the logging right and all that other stuff. So, the actual messaging takes, what you said, 2 weeks or a month or something like that, and then, 6 months to ship the product. I think that's a fairly typical story. So this is up there, it's running, it's in production. So what did they learn? What are some lessons that they learned from doing this that we should pass on?
I think like all customers, actually, this is not just Amazon Music. There are many other customers who are in the platform. One of the important lessons that they've learned before going into production is to make sure that they actually do a load test with the service. And to make it clear here, the load test is not really to test whether AWS IoT can scale for their requirements. It's more around, what is the behavior of the clients when they interact with AWS IoT at this massive scale. And customers have usually run into problems around handling exceptions or the retry logic. I mean, you're familiar with how wrong people can get with retry logics and stuff like that. We talked about it in our previous Twitch sessions as well. And throttling scenarios, how do you handle those throttling scenarios in a graceful manner for your customers? So those are some of the learnings that they got. In fact, Amazon Music actually uncovered a bug while they were doing a load test to see that their clients were actually spending a lot more time in processing their messages on the client side, which eventually led to a much higher fan-out latency, even though the server was, like the AWS IoT server was processing messages pretty fast. There was also another customer who had an interesting story where they launched this service, they launched their application in production, and then they noticed that they had like significantly more volume of messages coming in than what they had anticipated. And this was because of a configuration bug that they had in terms of how they set up their topics and the subscribers. So some of these bugs that we're talking about here, they're very hard to kind of uncover during a functional test under low volume. You want to kind of run your system at high scale to see, some of these things that would prop up. And many of our customers now have learned this lesson, some in the good way and some in the hard way. But one of the big important lessons learned is to make sure that customers are able to doing the load tests before getting into production. So that's
Yeah,
one.
I'm going to pile on and just echo what you said and add some more emphasis to it. And let's not kid ourselves. Load testing is hard, right? Let's not, it's something you've got to do, and it's something that has the potential to delay your launch because, you absolutely should not launch until you've done real load testing. And load testing takes a while to set up the infrastructure, set up your fake transaction generator, whatever it is. But software that's processing 10,000 events and software that's processing 1 million events are just qualitatively different. It's not just a matter of multiplying the throughput by n. Things happen, weird stuff happens, both on the client side and on the server side. And you said, and they didn't really need to. It's not as though they needed to test the throughput of IoT, but yeah, they did too. They actually had to test the throughput of the client, of the intervening AWS service, and of course of their server. And actually, my experience is that things usually break on the server before they break on the client. But they break somewhere. It is absolutely certain that the first time you take your shiny new software that you've built and you crank the load up to like really large scale, something will break. So you really, really want that to happen when you're load testing, not when you have your splashy first launch of your new system. There was something you said earlier when we were talking about compression, right?
Oh, yes. So the other lesson that they learned, is that, so they did, because they were doing like all the math stats for games and stuff like that, they had huge payloads, even for IoT's perspective. So one of the things that IoT builds you is we meter at 5 kilobytes of increments. So one of the things that they did was they actually compressed their payloads, which helped them not only in terms of performance, but also like reducing their payload size and their overall cost. So if you are able to compress your payloads, and if you especially have large payloads, I would highly recommend that to cut down your cost of usage of AWS IoT.
Yeah, I'd probably be even stronger than that. I'd say if my messages were any longer than just like 100 bytes or so, I'd probably consider compressing them by default. Not only are you going to save money on the network billing and our billing and so on, but compression and decompression is way faster than the network. These applications, to be brutally honest, are sitting there 95% of the time waiting for the bytes to trickle in over the network. And if you can send fewer bytes and then decompress them once you get them, you're just going to get better performance end to end. So my instinct for this kind of application is, always compress unless you can prove that it won't work for some reason. Okay, now we have a tradition here that you can't get off the show until you've shown us some code. So you got some code for us to look at?
Yep. So the code that I'm going to show is basically it's actually a chat application that we built on top of AWS IoT, and I'm going to emphasize more on the authentication part that we talked about and how this chat application used authentication to be able to kind of talk to AWS IoT. But before I jump on the code, I'll just do a quick glance of the architecture itself. So if you see here, so these are basically the applications, desktop or mobile application. We're using Google or Facebook identity providers as federated identities. For the AWS services, AWS IoT to kind of publish to a particular chat room, devices can subscribe to those chat rooms and they would receive the message. So there's also API gateway backed with AWS Lambda. This we basically use for kind of doing a bunch of APIs that we need for the chat application, like registering a user or creating a room and so on and so forth. But one important thing about here is this API flow is also used to attach IoT policies to the federated identities. And then, of course, AWS Cognito to get the authentication user pools and the identities as we talked about. And lastly, S3 and fronted with CloudFront to kind of vend out static content or static assets. So jumping over to the code, the way I'm going to run this through is first, basically, I'm going to talk about a bunch of resources that we have to create to make this happen. And I'm going to emphasize again on the authentication aspect of it. So this is this
looks like a CloudFormation file, right?
That's correct. So this is a CloudFormation template. Here's where we kind of generate a bunch of static resources. So I'm going to skip over the first two, which is DynamoDB tables that we kind of need for like running the chat room and the history of the chat and all that stuff. I'll skip over that and then highlight on these. So this is the connect policy. So this is the IoT policies that I was talking about, where you can basically attach them to the principals or the identities to make sure that the device has fine-grained access. So here basically we're saying this policy will allow IoT Connect operation. Similarly, there's a subscribe policy, very similar. The only difference there is that you can actually even fine-grain it to the exact resources that you can subscribe to. So in this case, we basically say that they can subscribe to this topic filter, room, public, followed by any suffix. And then there is the receive policy, which is very similar to subscribe. So one thing to note here is that if your IoT device is receiving messages, then you basically have to make sure that your device is first subscribing to those topics and also has a policy to actually receive messages. And then I'll jump on to the resources for Cognito. So this first one is basically you're creating a user pool for your Cognito identity, and then you basically create this app client as part of that user pool. And then you create what we call as the identity pool, which is basically a group of identities that Cognito can vend out that you can use to get access to AWS services. And as part of that, you basically say, hey, you support Facebook, Google, so federated identities are supported as part of this user identity pool. And then the main stuff here, which is the identity pool auth role. So this is basically like an IAM auth role that you define, which you provide access to for anybody who has the identity pool access. So in this, we're basically saying that for this auth role, you have access to AWS IoT data plane, and then you also have access to the API gateway APIs here. And that's what you basically give access to the Cognito identity pool. And then finally, you basically have to do one last thing, which is to kind of attach the identity pool auth role to the identity pool itself. So that's all about the CloudFormation setup to create these static resources. Then jumping onto the code. So this is the first code that you can start with. This is basically the Cognito code, where you basically create the user pool. And from the user pool, you get the current user from here. And once you get the current user, you basically use that to get the user token. This is basically a Cognito API to get the token and from the current user itself.
And now this would allow like federated identity and different sign-in modes and so on?
That's right. Once you get the token, you can use that token to fetch the temporary credentials. And that's the function here, where you can give a token, and then you can say who the federated identity is.
Facebook, Google, Amazon, got it.
That's correct. Or you can use just the Cognito user pool itself.
Sure.
And then you get the AWS credentials from there. There you go. Yep, if you see the case statement here. And then once you got the identities, you basically have the access ID, secret key, and then the session token. You use those to kind of create now the IoT client itself, which basically can talk to AWS IoT. So in order to create the client, you use the device SDKs that AWS IoT provides. So you can use the device SDK and then create like a device, which essentially kind of vends out the IoT client. So as part of that, you can set the region, the client ID, which needs to be unique across all your devices within an account, so that you can set that up. You can specify the protocol. There are a couple of timeout configurations and reconnect time configurations there. And then the key part here, which is the access ID, secret key, and the session token that we got from Cognito. So with this, you basically are essentially giving your IoT client the AWS credentials to talk to IoT. But one of the things that developers actually miss out on is that this alone is not enough for your device to actually make a successful connection to AWS.
So Dinkar, this, just to be clear, this is all the code that's on the client, right? It's on the mobile phone or whatever.
This is all on the client, yes.
Right.
Right. And the thing that I was talking about is, now that you've attached the client, what you actually need to do is to give that fine-grained policies to those individual Cognito identity IDs, so that your device can now actually do the operations that you want it to do. So remember, we created the connect policy in the CloudFormation template, so we could use that policy to fetch that policy here, and then you use the IoT control plane APIs to kind of say attach principal policy, and you give the policy name, and then the principal itself. The principal here is basically is the cognito identity ID itself.
Okay.
So once you do this, yep.
So two things. Now that we've done, so first of all, Mr. Wi-Fi Beef asks, how big is the SDK? I have no idea, to be honest.
I'm not sure either, but we can find out.
Yeah, okay. Neither of us know off the top of our heads, Mr. Beef. So maybe one of the people on the moderators can go look it up. Oh, and the second question is JavaScript the only language you can use with the device SDK? No. The SDKs come with all the languages you've ever used, and I don't think we have Haskell or Erlang, but most popular languages just work with this. Okay, so the next question I had is, now that we've seen 3 screenfuls of setting up the authentication, can we see some actual messages?
Yep, we can. And then just before going that, Tim, I just want to show one interesting policy aspect as well before we jump onto the message itself. This one is basically like we saw the static policies that we created, but this is a dynamic policy that you can actually create. So you can say, hey, this device can only publish on this particular topic. So in order to do that, in this case, we basically create a dynamic policy using and by basically appending the identity ID itself, the cognito identity ID itself to the topic. And so what this basically means is that now you can restrict that device to only publish on that topic. And yeah, to your point about showing up the actual code to publish message itself, it's pretty straightforward, and that's the reason why we were not emphasizing on that here. It's basically like one-line code. Once you get the client, you use the publish API to give the topic and the payload itself. Similarly for subscribe and unsubscribe.
And then how do you receive a message?
Yep. So for receiving a message, you basically kind of attach straightforward callbacks of message handlers that you can attach on message received. So, and then you can use the message handler to code up whatever implementation you have on what to do with those messages. That's pretty straightforward in terms of what that message handler looks like.
And this, folks who are listening, if you've done cloud applications, this won't surprise you. But if you haven't, this is just the way life is. Is that we live in a security-centric world, and getting authentication and authorization correct is super important. There's nothing more important than that. And so it's quite typical that you have 3 screenfuls of code to set up the authorization, authentication, security policies, and then half a screenful of actually doing the work. Okay, I think we've pretty well covered this story. Is there anything else you wanted to add, Dinkar, before?
No, I think that's about it. Yeah.
Okay, let me see if there's any other questions. Somebody's come up with an. There's a link to the SDK page. Presumably the slides will be there. The size of the SDK will be there. So in that case, thank you, Dinkar, and thank you, everybody. And this, by the way, is the last of our 7, I believe it was, sessions on different messaging technologies offered by AWS and how and when you might want to use them. And the URL you see right there on the screen right now, AWS Amazon.com/messaging/Twitch, has recordings of all these. And if you think you might want to use SNS or MQ or IoT, I strongly recommend going and spending half an hour or so watching one of these previous broadcasts. And it's quite likely that you'll find somebody there talking about their problem, and it may help you make more clear decision on how your trade-offs are going to work with that technology. I guess as we go on and our applications become more cloudy, more cloud native, more distributed, we realize that basically everything non-trivial needs messaging. You can't possibly build a modern distributed application without some messaging component in it somewhere. If you want a little bit on the background and philosophy of that, the very first in this series, which I did with Jeff Barr, has some general discussions of why messaging matters and why you actually need it in more or less any modern cloud-native distributed application. And with that, I will check to see if there are any more questions, and I don't think there are. So thank you, Dinkar. Thank you, everybody, for listening. And this has been great. And somebody asked what's going to be on Season 2, and that's a good question. We should have a Season 2. Maybe we should do, databases or compute modes or something like that. There's lots of places where we could use surveys. So until Season 2 then, thank you, everybody, and goodbye.
Bye-bye.